Welcome to this video on preparing reaction mixtures for initial rates experiments, and this will apply to any time when you're mixing different reagents in solution to try to get specific concentrations. So let's begin. So here are some principles just to begin with. Imagine we're studying this reaction where A is going to react with B to form C and D, and all of these reagents here are aqueous. And the intention here is that we're going to carry out several runs with different initial concentrations of A and B. And I'm going to use throughout the notation for concentration, I'm going to use square brackets A, and as it's the initial concentration, A naught, and similarly for B, B naught. Now, how are we going to accomplish that? Well, we're going to vary the concentrations of those by adding different volumes of stock solutions of A and B to the reaction mixture. Now, in order to make sure that we don't start the experiment before time, we're probably going to have to make sure we've got our stopwatch ready when we're going to add one or the other. But the idea here is that we're going to use what are called stock solutions. And these are concentrated solutions of A and B, higher than any concentration we want to actually use in the experiment. And therefore we can dilute those to produce the required concentrations of A and B. And we'll see how that works in a minute. Now, it's really important when we do these experiments that we only vary one concentration at a time. So between any two runs there should only be one concentration which changes, or perhaps rather saying that if you're going to have a just between runs only one substance should vary, and that implies that your results will be valid. If you don't know, if you have both concentrations changing, then you don't know which substance, A or B, had the effect that you see. And finally, we're going to keep the total volume constant, and we'll discuss why that's useful later. And for that, because we've got aqueous situations here, we've got everything dissolved in water, by adding distilled water where necessary. So water won't actually add any of our reagents, but it does sort of pad the solution out so you keep the total volume constant between the runs. So let's have a go at actually trying to do some of these calculations. So here, a situation we have some stock solutions of A and B with these concentrations, and we want to do in our first run 16 centimeters cubed of A and 4 of B. And I've depicted this situation here. We've got 16 of A, it's here, 16, and B is only 4. And so the total is 20 centimeters cubed for the solution. Now the question is, what is the concentration of A in that reaction mixture at the start, and what is the concentration of B once we've mixed them together? And in order to do that, we're just going to think about each one separately. So let's think about A. Now in this situation with A, the B that was added, which is represented here, this 4 centimeters cubed of B, that 4 centimeters cubed of B doesn't have any A in it. So it may as well be as if you've added water to A from the respect to the concentration of A. And so these problems here where we're trying to work out the concentrations in a reaction mixture is basically the same as a dilution problem, because there was no A in the B that was added. So in order to work out the concentration after this dilution, we need to realize that the number of moles of A before dilution, so in the stock solution, and after, is exactly the same. So we can work out the number of moles that was in the stock solution because we know both its concentration and its volume. And so if we do use our typical formula of moles is concentration times volume, then we can work out 0.1 times 16 times 10 to the minus 3. You've got 1.6 times 10 to the minus 3 moles in the stock solution. And that's exactly the same as the number of moles that you've got in the reaction mixture as well. And so to work out this concentration, we just reverse that formula and do concentration is number of moles divided by volume, and we find that our answer is 0.08 moles per decimeter cubed of A. Let's switch to thinking about B now. So remember, it's almost like wearing a special pair of glasses that can only see B. In all of that A that was added, the stock solution of A, there was no B molecules, and therefore B, that was essentially just like adding water to B. So we can play the same game again. We know the concentration and volume of the stock solution of B, and so we can work out the number of moles, again using concentration times volume, and we find 2 times 10 to the minus 3 moles of B present. And then we imagine that that B is going to be spread over the whole mixture now, and so that 2 times 10 to the minus 3 moles, in order to get the concentration, we do moles divided by volume, and we find that we've got a concentration of 0.1 moles per decimeter cubed. So there we have it. That first run, 16 of A, 4 of B, those are the concentrations we've just worked out. Now what we need to try and do is to do the more common problem where we want a specific concentration and we need to work back to the volume that we need. So finding the unknown volumes. This is a bit of a harder problem, but we can just use exactly the same methodology as before, but now we're doing it in reverse. We know that from the perspective of A, we've got this concentration and this volume in the reaction mixture, and we know that we've got this concentration of stock solution. So now we can work out the number of moles that were in the reaction mixture just by doing concentration times volume, and we find that we need 1.2 times 10 to the minus 3 moles of A. Then we now need to work out the unknown volume, so we can use our N equals CV formula. We rearrange that to find the volume is number of moles divided by the concentration. And so when we do this divided by the concentration, we're going to find that that is 12 times 10 to the minus 3. And that's in decimeters cubed. So if we want this in centimeters cubed, it's just 12 centimeters cubed. Now when we come to doing the volume of B, we actually don't even need to do that, because we can see that for B, we've got the same concentration required in run 2, and therefore the volume will be exactly the same. Now remember, at the top here, we're trying to keep our total volume constant. This was adding up to 20. At the moment we've only got 16 here, so we need 4 of water in order to make this up to a total of 20. So why not now pause the video and see if you can work out for the remaining runs what the volumes should be. Well, here are your answers. These are the volumes that we should have obtained for the remaining runs. And notice that for B, they're almost all the same except for that final one, which is a volume of 2, and this is the volume of H2O that you need. Now finally, just want to think about the importance of keeping the total volume constant using water. It's really, really useful to do that. And I hope you can see that from the numbers here. So you can do it without this, but there are 2 real advantages to that. And the first advantage is that if the concentration, I'll just use a different abbreviation, if the concentration stays the same, so does the stock volume. So when we were doing our second problem here, where we had to find the volume of B needed in the second run, because the concentration was the same, I knew that the volume of B had to be 4 again. If I hadn't put any water in, when I'd reduced A, I would have also had to reduce the B just to keep the same volume, just to keep the same concentration. But this way, the stock volume remains constant if the concentration remains constant. Now the second, and this is even more powerful, the volume, let's look at a situation, let's say here, where we've gone from, let's choose 4 and 5, where B has gone down by a factor of a half. Now notice here that the volume of B has also gone down by a half. Now this isn't an isolated incident. If I go from here of 0.08 of A concentration to 0.04, timesing by a half, then the volume of A has gone down by the same factor, multiplied by a half. And so the beauty of keeping the volume constant is that the volume of the stock solution needed is directly proportional to the concentration required. And that's really, really useful, because if we decide that we want half the concentration, we know we need half the volume. So once we've worked out the volumes for one run, we don't even really need to go through the complicated mole calculation. We just need to reduce our volumes in proportion to the amount that the concentration is reduced by. So here it's gone down, it's 3/4 of 0.08, and so we need 3/4 of the volume. And so this makes generating tables like this much, much simpler. You only have to do the moles calculations once, and then you can generate the other volumes much more quickly. So that's how you prepare samples with the right concentrations for initial rates experiments.